Welcome back to the Deep Dive. This is the show where we take the massive operational stack of the cloud and really just break it down into pure strategic insight.
Exactly.
And if you're listening right now, maybe you're a junior DevOps engineer, you're studying for your certification, or maybe you're trying to navigate that, that wave of information that comes with cloud native.
It's a lot.
It is a lot. But this deep dive, this is your shortcut. We are not just here to memorize a list of services. We want to understand the architectural philosophy behind them.
And today we're focusing squarely on the operations and monitoring domain. So our mission, really, for you, the listener, the learner, it's critical. We're moving beyond just reacting to failures.
The firefighter mode.
Firefighter mode, exactly. We're going to teach you how to architect resilience and financial efficiency directly into your infrastructure from the start.
I love that. It's the shift from being a constant firefighter to being a system designer. An architect. Absolutely. In our conversation today, it's really built around two, I think, foundational concepts. So first, we're going to tackle automation, that SRE mandate to get rid of manual toil. And second, we're diving into strategic resource allocation.
Yeah.
Which, in plain English means how do we make these reliable systems vastly cheaper without giving up too much performance?
Right. It's that balancing act.
It is. But before we get into the meat of it, let's just quickly define our foundational unit. It's central to everything we're going to talk about, the VM.
Right. So a VM, or a virtual machine, is, well, you can think of it as a fully functional, self-contained computer running inside the cloud provider's giant data center.
A server, but it's software.
A logical server, exactly. It's defined by its CPU, its memory, its operating system, and it's what runs your application code.
Huh.
So in our discussion today, every single architectural pattern we explore, whether it's self-healing or, cost optimization, it's all applied to fleets of these virtual machines.
Perfect. That sets the stage perfectly. Because, running one VM is easy. The hard part is keeping it running reliably, affordably, and automatically.
Yes.
Our goal here is to make sure you stop spending your time manually keeping those individual VMs from, exploding. That's the firefighter mode. And start designing systems that actually have the intelligence to fix themselves.
That's the dream.
So let's anchor this whole thing in a scenario that I think every single operational engineer has faced at some point.
Oh, yeah.
You're supporting a crucial production service. Maybe it's an internal API. Maybe it's some heavy back-end worker doing data processing. But the critical detail is this. It's running on a single compute engine instance.
The dreaded single instance.
The dreaded single instance. And here's the daily problem. It crashes. And not gracefully. I mean, it goes down hard. Maybe it's a memory leak, a runaway thread, something.
Something triggered by a weird payload you didn't expect.
Exactly. But it fails regularly enough to guarantee that you, the junior engineer, are getting paged at 3 in the morning.
And that is the operational reality, isn't it? In the early stages of a lot of companies, or, even with older services and bigger ones, they have one server.
Right. They prioritize speed.
They prioritize speed of deployment over resiliency. And when that server fails, the service just stops. Dead. The business impact is immediate.
And what follows is the painful manual process,
Yeah.
the toil that we're here to eliminate today. You get that alert.
Your phone buzzes.
The phone buzzes, you triage the failure, you log in, you confirm the instance is unresponsive, and then you are forced to spend your precious time recreating the service.
And that time is so costly, it's stressful, and it's not productive at all. You're manually deleting the crashed instance. You're making sure that the broken state is wiped clean.
And then you have to manually provision and launch a brand new instance based on, that golden image you hopefully stored somewhere.
Hopefully. That whole cycle, from the page to the resolution.
Yeah.
It's just so time-consuming, and it's incredibly error-prone.
Why error-prone? Let's dig into that.
Well, think about it. You're performing this recovery under pressure. It's 3 a.m. You might forget a critical configuration flag, or you might misattach a network tag. Or
accidentally pick the wrong machine type, and suddenly the bill is twice as high.
Exactly. You're perpetually tied to your terminal, just performing this repetitive, low-value work. And the way an organization measures this is with a key SRE metric, a high MTTR. Or mean time to recovery.
Okay, let's unpack this further.
Yeah,
because this is really the core of the SRE philosophy. We need to understand why this manual process is considered a failure of design, not just, a nuisance of the job.
It's absolutely a failure of design. It violates the central mandate of Site Reliability Engineering SRE, which is, it's basically Google's philosophy on how to run huge systems reliably.
Right.
And the core SRE principle here is crystal clear. The goal is to reduce the time spent performing manual operations, that repetitive, mechanical, reactive work we call toil.
And instead of doing that,
You automate those failure responses completely. If restoring the baseline state of your service requires a human being to log in and click buttons or run scripts, your system is fundamentally brittle.
so it's not held together by good engineering.
No, it's held together by human exhaustion.
And that human effort is always the most expensive, the slowest, and the least scalable component in your entire architecture.
Without a doubt.
If we can just automate the recovery for, say, the top 3 failure modes, we suddenly free up all this engineering time to go back and figure out why the failures are happening in the first place.
Which is the truly high-value work.
That's the real work. So I see the principle, but practically speaking, what's the hard boundary? How do I know if I'm spending too much time on toil, especially if I'm a junior engineer?
A good rule of thumb that comes from the SRE literature is the 50% rule. Engineers should spend no more than half their time on operational work, the toil.
And the other 50%?
The other 50% should be on development or strategic projects, building new things. So if you are constantly performing manual recovery, you are way over that boundary.
Okay.
For your certification exam or just for designing your next service, the red flag should always be the same. Just ask yourself, is a human being required to execute the immediate fix for this common failure?
And if the answer is yes?
If the answer is yes, you're accumulating technical debt in the form of toil. We need a system that lets you define the desired state.
So something like, I need one healthy instance running my code and serving traffic on port 8080.
Exactly like that. And then the system needs to automatically, relentlessly, and tirelessly enforce that state for you.
That distinction enforcement versus manual intervention, that feels like the key takeaway.
It is. A robust operational practice, guided by SRE, dictates that these common repetitive recovery steps have to be codified. They have to be automated.
Your time should be spent debugging the root cause or building the next feature.
Not executing the same delete and create commands for the 10th time this month.
Right. That sets us up perfectly for the solution. Because if manual recreation is the problem, what is the fundamental architectural pattern that gives us the SRE-friendly fix?
The definitive solution for this exact problem, reducing manual ops, minimizing that MTTR, implementing self-healing, is the Managed Instance Group, or MIG. And you combine that with precisely configured health checks.
Okay, MIGs.
This is what moves you from being reactive to being proactively resilient.
Let's define what a MIG is, because this is where I think a lot of learners, they stop short. They hear instance group, and their brain immediately jumps to auto-scaling for high traffic.
Right, for Black Friday.
For Black Friday. And while that's true, it kind of obscures the foundational immediate benefit we're talking about right here.
It really does. A MIG is, fundamentally, it's a control plane, a resource manager. It oversees a collection of identical virtual machines.
Yeah.
It makes sure that all the instances within that group stick to a predetermined configuration. And that configuration is defined by a central thing called the instance template.
And while it does handle scaling, letting you add or remove VMs based on load, its most critical function for our scenario is state management and self-healing.
That's the core of it.
So let's pause on that. The instance template. You mentioned it's essential. What exactly does it capture, and why is it so vital for this automated replacement process?
The instance template is the blueprint. It is the single source of truth for every VM created in that MIG. It's a locked configuration that specifies, well, everything you need to recreate an instance perfectly.
Like what?
The operating system image, the specific machine type, like an N2 standard 2 critical metadata, SSH keys, network tags, firewall rules.
And crucially, the startup script.
And most importantly, the startup script. This template guarantees that when the MIG needs to provision a replacement, it's creating an exact, non-drifted replica of the original healthy server.
So if I go in and tweak a setting on a running VM,
The instance template doesn't care. The replacement will revert back to the original, secure, golden configuration. It prevents configuration drift.
that's the beauty of it. It forces consistency. And the key nugget for our junior engineer is that even if you only need one server,
Just one.
putting it inside a managed instance group dramatically increases your resilience.
Yeah.
The MIG's primary function in this self-healing scenario is maintaining a configured size of one healthy instance.
Precisely. The MIG is the policy enforcer. It enforces the desired state that's defined by the template and the group size. But To enforce that policy, it needs data. It needs accurate, continuous data on the status of the VM.
And that's where the health checks come in. They're the sensor.
They are the sensor, exactly.
So let's dive deep into the role of these health checks. We're past just doing a simple ping, right? What are these checks actually looking for?
Right. This is much more than is the machine on. Health checks are a continuous diagnostic tool, and we use different types depending on what the application needs. The two most common are,
Okay.
first, a TCP health check. This just makes sure the operating system has loaded and that your application is listening on the required port. It's basic network connectivity. Is anyone home?
Is the light on?
Is the light on? But the second one, the HTTP or HTTPS health check, this is the gold standard for application health.
Why is it the gold standard?
Because it typically probes a specific path, maybe something like health or status, and it expects to get a specific HTTP response code back, usually 200 OK.
So it's not just checking if the server is on. It's asking, are you actually ready to do work?
Precisely. It confirms the application process is running, the web server is responsive, and critically, that the application logic itself is functional and ready to serve real traffic.
And this check just runs over and over.
Continuously. It monitors the instance's responsiveness based on parameters you configure, how often to check, how many failures in a row mean it's unhealthy, and how long to wait for a response.
Okay, so the health check is the eye, rigorously defining whether the VM is actually delivering business value. And the MIG is the brain and the muscle ready to act.
A perfect way to put it.
Now, let's detail that crucial automation loop. Let's walk through it step by step, showing how it completely eliminates the junior engineer's toil when that server crashes.
Okay, so the loop is deterministic. It runs without any human intervention, which is what ensures that rapid recovery. So, step one.
The crash.
Failure event. The production service crashes. The memory leak finally takes it down. The process dies. Something goes wrong.
Okay, what's next?
Next is the detection cycle. The health check starts trying to probe that health endpoint. It fails. It tries again. It fails again. After a few repeated failures, it exceeds the threshold you configured.
It declares the instance unhealthy.
The health check determines the instance status is officially unhealthy. Then, step 3 is state reporting. The health check reports this unhealthy status back to the managed instance group controller.
So the eye tells the brain, we have a problem.
Exactly. Which leads to step 4, policy enforcement. The MIG is configured to maintain a desired size of one healthy instance. It's constantly in a reconciliation loop checking the state.
And it sees a mismatch.
It sees a mismatch. The current state is one unhealthy instance. The desired state is one healthy instance. They don't match.
And this triggers the final step, the action.
The self-healing action. This is the toil elimination. The MIG immediately performs that SRE operation for you. It marks the unhealthy instance to be terminated, and in parallel, it provisions and launches a brand new replacement.
From the instance template.
From that definitive instance template. Once the new instance is up and running and it starts passing its own health checks, only then is the failed instance finally deleted. The system recovers itself.
And how long does that usually take?
Minutes, usually. It really just depends on the boot time of your instance and your application.
And the entire time this is happening, the engineer is maybe sleeping, not manually intervening. The mean time to recovery is now dictated purely by the automated process, not by human reaction time.
That's resilience baked into the platform.
So that's the core insight for the listener, for the learner. The action here, it's fundamentally architectural. It's create a managed instance group with a single instance and use health checks.
That's it. The immediate goal is reducing toil and achieving true self-healing, regardless of whether you ever need to scale up to 2 instances.
Let's expand on that analogy we talked about before, comparing a MIG to a really organized store manager in a 247 operation.
Right. Think about it. You have a lead cashier that's a mission-critical role in a store.
The whole operation stops if they're not there.
Right. So if that lead cashier calls in sick unexpectedly, the entire point of sale doesn't just shut down until the store owner can drive in from home. That would be crazy.
That would be the manual process.
That's the manual process. Instead, the store manager, who is our MIG, operates based on a protocol. That's our instance template. They immediately call in a replacement worker based on a standardized procedure.
And within minutes.
Within minutes, the replacement is at the till performing the exact same function. And crucially, the manager isn't worried about why the first cashier is sick right now. That's a separate, long-term HR problem to solve later.
The root cause analysis.
Exactly. The manager's immediate operational mandate is just to ensure the desired state is met. And that state is one functioning cashier at all times.
And that's how you move from constantly being on call to actually, sleeping better at night.
Yes. You've outsourced the repetitive mechanical failure recovery to the infrastructure, and you let your highly paid engineering team focus on strategic improvements, not on being human cron jobs.
That's a fantastic transition. So we've achieved operational reliability. We've mastered self-healing. Now let's pivot. Let's pivot hard to that second major challenge for any ops team: financial efficiency.
The budget.
The budget. Our service is super reliable now, but the finance department is knocking on the door asking, we're running this huge fleet of servers 24/7. How do we cut this massive cloud bill?
And that's a question that always comes up, sooner or later. The goal is clear. The organization needs to dramatically reduce the unit cost of its virtual machines.
Especially for workloads that maybe don't need 100% guaranteed availability all the time.
That's the key. Standard VMs are expensive because you're paying for that guarantee. Guaranteed uptime, guaranteed resource allocation, predictable stability. You pay a premium for certainty.
Which leads us directly to the star of this section: preemptible VMs, or PVMs. For the learner, it's arguably one of the most essential concepts in cloud cost optimization. The savings are just so substantial.
They're huge.
So what is the core mechanism? What's the trade-off that makes PVM so attractive from a budget perspective?
The core mechanism is a very direct trade-off between price and resource guarantee. PVMs are offered at a steep discount. We're talking 60% to 90% less expensive than their standard counterparts.
Wow.
But here's the catch. You get that discount because you agree to surrender control over their lifespan.
What does that mean, surrender control?
It means you are deploying your resources into the cloud provider's excess capacity, their spare capacity. And Google Cloud can decide to terminate or preempt that VM with very, very short notice.
And that notice period is a critical technical detail. I think for any certification prep, you have to know this number. We're talking about a 30-second warning, right?
Exactly 30 seconds. When the cloud provider needs those physical resources back, maybe a standard full-price customer needs capacity, or they're doing internal maintenance, your PVM gets a notification.
Through its metadata service.
Through its metadata service. And this is not a polite request. It is an imminent termination notice. After those 30 seconds, the VM is shut down. The resource is reclaimed. Gone.
So why? Why does a cloud provider offer such a massive discount on resources that are otherwise identical? They have the same CPU, same memory.
They're monetizing their latent capacity. A cloud data center is designed for peak utilization, but it's almost never at 100% across the globe, 247. PVMs allow them to sell off those temporary, otherwise wasted compute cycles.
It turns spare capacity into revenue.
Right. But the instant a paying standard VM customer needs those resources, the standard customer takes precedence and your PVM is sacrificed. It's a dynamic, low-priority tier of compute.
Okay, so we achieve massive cost savings by accepting a fundamental reduction in guaranteed availability. This is not for systems where even a brief interruption would violate a service level agreement, an SLA.
That is the crucial distinction. You cannot just sprinkle PVMs everywhere and hope for the best. Using PVMs is an architectural choice. It means you must be deeply familiar with your application's tolerance for interruption.
The cost saving is enormous.
But the trade-off is unavoidable: sudden, unpredictable termination. And that translates directly to reduced service level indicators, or SLIs, like uptime or request success rate.
Let's really solidify that trade-off with the analogy we talked about. PVMs are like buying a standby ticket for a flight.
Yes, think about that. You're trying to book a complex international flight. You show up at the gate, you ask for a standby ticket. It is significantly cheaper than a reserved seat.
And why is it cheaper?
It's cheaper because you have to accept the risk that if the flight is full and every standard full-fare ticket holder shows up, those are our standard VMs, you might get bumped off. You might be preempted entirely.
You save a lot of money, but you sacrifice certainty.
Exactly. You have to be ready to walk away and try again on the next flight without penalty. And this reflects the PVM model perfectly. Saving money comes at the expense of a guaranteed departure.
This choice really pushes operational planning beyond just technical deployment. It becomes strategic cost architecture. You're actively searching for parts of your infrastructure where you can afford to introduce some intentional instability to save money.
Without jeopardizing the core business objectives. And this choice, it requires a mature application architecture, which brings us to a key principle, decoupling.
What do you mean by that?
If your PVM is preempted, any data or state that's stored locally on that machine in its memory on its disk is instantly destroyed. It's gone.
So you have to have a plan for that.
You must have mechanisms in place to handle that failure gracefully, which I think we should explore that right now.
That transition leads us directly to the key architectural question then. Given this inherent risk of preemption, the 30-second warning, which types of applications are actually suitable for PVMs? And what does the application have to do to survive being constantly killed?
The prerequisite is non-negotiable. The application must be fault-tolerant and ideally stateless.
Let's define fault-tolerant in this context.
Fault tolerance here means the system can handle an interruption gracefully. When that 30-second termination notice arrives, the workload has to be designed to either save its current progress, we call that a checkpoint, or cleanly exit.
Or just be okay with the job being picked up later and restarted from the beginning.
Right, without catastrophic data loss.
And we have to emphasize that data persistence is crucial here. If a PVM gets preempted, anything stored only in its local memory or on its temporary disk is just gone.
It's gone forever. Fault tolerance necessitates separating the compute layer, the PVM, from the persistent data layer, like external storage.
So let's focus on the ideal use case that the source material gives us. It acts as a great template for how to use PVMs. A GPU-accelerated video rendering platform that retrieves input and stores output videos in a storage bucket.
This is a perfect example. It exemplifies a fault-tolerant, batch-oriented system.
Okay, let's break that down. Why is this specific workflow GPU rendering with decoupled storage the poster child for preemptible computing? What is the underlying logic?
It really boils down to two core architectural concepts that make the PVM model work. The first is decoupling, and the second is external orchestration.
Okay, let's start with decoupling.
First, decoupling from storage. Notice the job description. The platform retrieves input data from a persistent, highly available storage bucket, like cloud storage.
And then it saves the result back to that same bucket.
Exactly. It stores the final result back into that bucket. The GPU-accelerated PVM itself is just a temporary processor. It's ephemeral. It holds no long-term critical state.
So if the VM just vanishes mid-process,
The input data is still safe in the bucket, and the output data, if it was already saved, is also safe. The compute resource is disposable. That's the key.
okay, that makes sense. What's the second concept? External orchestration.
Right. This involves batch processing and checkpointing. Video rendering is usually a huge, time-consuming batch process, so smart architects break it down into discrete, independent work units.
Like render 1 minute of video at a time or process a single sequence of frames.
Exactly. So if the PVM is preempted mid-render, the key is the job scheduler. There's an external system managing the work.
So the architecture needs some kind of middleware layer, something to track all the jobs, like a service, maybe pub/sub, or just a dedicated queue.
Precisely.
How does that external orchestration handle the PVM termination then?
Okay, so let's say a PVM is rendering a 10-minute segment of video. It gets that 30-second notice. Ideally, the application is written to use that time to save any current progress, a checkpoint to the storage bucket.
And then it signals back to the queue.
And it cleanly signals back to the queue or the scheduler that it's shutting down. Now, if the application doesn't checkpoint, or if it just fails hard,
Then what?
the job scheduler sees that the task was never marked as complete. The message in the queue times out, or the scheduler just recognizes the worker vanished, so the job item is automatically requeued.
And a new PVM, or maybe a standard one, gets provisioned to pick up that same task and start over.
And it either restarts it from the last known checkpoint or from the very beginning if no checkpoint was saved.
And the cost saving just dramatically outweighs the occasional inefficiency of restarting a segment.
Completely. You might lose 5 or 10 minutes of compute time every time a preemption happens, but you're saving 60, 70, 80% on the hundreds of machines running in that farm 24/7.
The trade-off is just. It's financially a no-brainer for that kind of workload.
Absolutely. This architecture lets an organization scale its rendering farm massively for peak demand, say, during a big marketing campaign, without committing to the full financial weight of a standard fleet. It's an efficiency gain that comes from embracing instability.
Okay, to really solidify this for the junior engineer studying for their exam, let's contrast this ideal use case with workloads that are an absolutely terrible fit for preemptible VMs.
Yeah, this helps define the boundaries, what not to do.
Exactly. Where is the unacceptable risk?
We can categorize these unsuitable workloads by the type of operational violation they represent. So, first up,
Go for it.
public-facing, latency-sensitive websites. This is a violation of your SLOs.
Explain that.
If your front-end web server is a PVM and it gets preempted, the user who is actively browsing your site, they immediately get a network interruption, a 503 error, a timeout.
The experience is just ruined.
It's ruined instantly. And since most public-facing services have strict service-level objectives, SLOs around latency and availability, like 99.9% uptime, using PVMs would just instantly violate those guarantees.
Okay, so no user-facing web servers. What's another bad fit?
In-memory caching systems. Think Memcached or Redis. This is a violation of data consistency and speed.
How so?
These services are designed to store critical, frequently accessed data like user sessions or database query results directly in fast RAM for speed. Preemption means instant, total data loss in that cache.
And then the whole system slows down.
Massively. The subsequent delay caused by the system having to rebuild the entire cache from the slower, persistent database. It completely defeats the purpose of having a cache in the first place. It creates a cascading performance bottleneck.
Right, and what's the third example?
Database clusters requiring strong quorum. This is a violation of consistency.
Okay, things like PostgreSQL with replication or clustered systems.
Exactly. These databases rely on a consensus mechanism, a quorum, which depends on predictable membership in the cluster. If a VM in that cluster gets preempted, it disrupts the consensus.
The cluster could lose a required replica.
Right, and that might force an election for a new primary or even put the cluster into a read-only state until it can stabilize. This violates the core principles of strong data consistency and guaranteed availability.
So the decision-making rubric is actually pretty simple then. If the workload is stateless, can restart quickly, and saves its data externally, like our rendering job, it's a PVM candidate.
And if the workload is stateful, demands high uptime to meet SLOs, or relies on in-memory speed.
Stick to standard VMs, regardless of the cost.
Exactly. It's an architectural decision that has to be driven by the requirements of the application first, and only then is it a cost decision.
And can we go a little deeper on that 30-second window? How do teams actually use that?
The successful use of PVMs in production often relies on a very specific configuration. You use a shutdown script that gets executed the moment that preemption notice is received.
And that script's only job is?
Its only job is to do something useful in those 30 seconds. To signal the external job queue, hey, I'm dying, someone else needs to take my work. Or to upload a final checkpoint. Mastering that 30-second grace period is the difference between a graceful failure and a catastrophic data loss.
That level of detail really confirms the architectural maturity you need. You're not just using a cheap VM. You are actively engineering for failure.
Yeah.
You're embracing controlled chaos.
That's a great way to put it.
This has been an incredibly focused, really technical deep dive into the operational backbone of modern cloud systems. And it's designed specifically to arm you, the listener, with the architectural understanding you need to pass that certification.
And more importantly, to build resilient systems in the real world.
Absolutely.
So let's just quickly synthesize the two core operational pillars we discussed today, because they really do represent the future of cloud operations. First, we covered MIGs and health checks. This is the non-negotiable foundation for self-healing operations. It's the strategy for minimizing your mean time to recovery, and it's the primary way you eliminate manual toil. It's a cornerstone of SRE.
And remember, the key takeaway is that you use a MIG not just for horizontal scaling, but fundamentally for resilience and automated failure recovery, even if you only have one instance.
Even with the size of one. And second, we covered preemptible VMs, PVMs. This is your strategy for achieving extreme cost optimization, often saving 60% or more.
But that saving is achieved by deliberately accepting the risk of preemption. So PVMs are only suitable for workloads that are fault-tolerant, stateless, and decoupled from local storage.
Typically batch-oriented, like that GPU-accelerated video rendering pipeline we talked about.
Understanding the why behind these features, why the MIG automatically reconciles state, why the PVM is cheaper but unstable, that's what separates a command line operator who's just following a tutorial.
From a true cloud architect who designs for efficiency and for survival.
Which brings us to our final and maybe most provocative thought for you, the junior engineer who's ready to tackle the cloud's toughest challenges. This is where these two powerful concepts intersect.
If you run a massive batch-oriented system, like that rendering pipeline,
Hmm.
could you strategically combine these two patterns?
Think about that carefully. Could
Mm.
you use preemptible VMs inside a managed instance group?
Ooh, now that's interesting. The PVMs would deliver that massive financial advantage, but they are guaranteed to fail, frequently and unpredictably.
The managed instance group's self-healing capabilities are designed specifically to handle instance failure and replace them automatically.
So this combination, it creates a volatile yet supremely efficient infrastructure. The MIG turns the inherent instability of the PVM into a predictable, manageable input for its self-healing automation loop.
The complexity introduced is significant, though. You'd need really robust quota management to make sure you can replace those failed PVMs rapidly.
And you'd need aggressive auto-scaling policies to compensate if a whole bunch of your PVMs get preempted at the same time.
But the financial reward for mastering that strategy is enormous. That combination, using cheap ephemeral resources and relying on robust SRE-driven automation to maintain the desired state.
That's not just an optimization. It's where modern cloud finance meets truly advanced operational architecture. That's a next level of thinking you need to embrace.
Go and explore how those components work together. Look into how you would tune the provisioning quotas and the instance templates for a fleet that is designed to be volatile.
That knowledge will make you invaluable.
Absolutely. Thank you for joining us on this deep dive. Go apply these operational insights, and we'll catch you next time.